Hey everyone, welcome back to my channel. How's it going? In today's video, I'm going to continue solving probability theory challenges and we'll go through step by step a few very interesting problems just to strengthen your understanding of the key concepts of probability theory. So without further ado, let's jump right in. All right, so you should actually be able to see the little excerpt here on the screen. I will just place it somewhere here or here on my screen. So you're going to be able to see the exact problem, the statement of the problem, and what you need to do, what you need to find in that problems. And so I hope that will be helpful for you. And let's kick it off. The first problem here is that we have a deck of 52 playing cards. Event A is that we are drawing the king, and event B is that we are drawing a club. The key point in this problem is that we are drawing only one card, and this is a very important part. So let's designate the first event A as a king and event B as a club. And so the first thing that our problem asks us to do is to describe the following events and compute its probability. So the first event here is the union of event A and event B. Well, from the description standpoint, that should be king or the clubs. So it could be any king from the deck of the playing cards, or it can be a club. So two possible scenarios, obviously. Remember, in our previous problems, we considered all possible outcomes, and we noted there might be a case when we have the overlap. So that's just the case when we have the overlap. For example, for the king, we have 4 cards of king in our playing deck, and this is the king, and we have 13 possible clubs, right? So one suit of playing cards. And that being said, we have one king of club, one king which is a club at the same time. So in other words, we have to subtract this overlap. And our total amount of possible outcomes should be something like P of probability A and B should be something like 4 plus 13 minus 1 over obviously 52. So that should be 16 over 52. And 16 over 52, if you reduce this fraction, you will get 4 and 4, 13, 4 over 13. This is the final answer. There is another way to calculate this, which is quite interesting. In order to calculate that, you can use the basic formula. Probability of A plus probability of B minus the probability of their intersection. What is the intersection of those events? This is essentially the event when both of them happens at the same time. Is that possible? Yes, it is, because they are not mutually exclusive. You can draw a king of club, as we just noted, because this is the overlap. So in that case, we have the probability of P of A equals to 4 over 52, and P of B is essentially 13 over 52. And now the probability of their intersection is 1 over 52. And hence we have A union B equals to probability of event A plus probability of event B minus the intersection when they happen at the same time, which would be 16 over 52. And reducing this fraction will give you 4 over 13, essentially the same result as we did before. So there are two possible ways to compute that. The first one is a little bit of a shortcut to calculate that, and the second one is more strict in terms of application of a strict probability formula, just following the basic formula for computing the probability. And the second thing that our problem asks us to do, which is the point B, essentially what we already found here, the intersection of those probabilities, we already found that. We found that this is our overlap, and that basically the probability of this event is 1 over 52. Now C, so here we need to find the probability of complementary of A, which is not a king, or this is club. So how to find this? Well, in probability theory, or in sets theory in general, there is such a thing which is called De Morgan law. De Morgan's law basically states that if you have two sets, let's say you have A union B, and you would like to find the complementary of those sets, you can write them as A complementary intersection B complementary. Or if you have the A intersection B complementary, that would be A complementary union B complementary. So this is the De Morgan law. There are lots of particular cases here. I'm not going to go over all of them. All you have to know here is that you can basically rewrite this expression as A complementary union B. If you take the complementary of this, we can rewrite this as A complementary intersection B complementary, and complementary of the complementary is essentially the set itself, intersection B. And you already know that probability of this event is essentially 1 minus the probability of its negation of its complementary, in this case the complementary of this, right? And so we already showed that this is the event A intersection B complementary. So rewriting this expression, we're going to end up with 1 minus probability of A intersection not B. It's a little bit easier to find because that means our king, which is not club. So which kind of outcomes we have here? Only three possible outcomes because the king, which is not club, three possible outcomes. So 1 minus 3 over 52, that would be equals 49 over 52. This is the final result. There is, of course, second way of solving that. We can just try to find the probability of A and union B as the probability of A complementary plus the probability of B. In the same manner, subtract their intersection and perform some computations here, and you will eventually arrive at the same result. You can try this by yourself. So the next thing that we have to do in this problem is to find the probability A complementary intersection B complementary. And again, we can apply the De Morgan's law here, 1 minus the probability of E union C, which is 1 minus, I'm sorry, not the C, the probability of B, 1 minus, we already calculated that 4 over 13, which would be 9 over 13. That's the final result. And now let's move on to the next point. So we have to find the probability of B minus A. So based on our previous axioms that we considered in our previous episodes, if you don't know what I'm talking about, feel free to get back to our previous videos and follow along from there. I'm going to show you that we can apply the axiom that we have already considered in our previous episode. So this is basically the probability of event B minus the probability of event A intersection B. The probability of event B is 13 over 52 minus the probability of their intersection 1 over 52, which is 12 over 52, which would be 3 over 13. That's the final result. All right, so this one is a little bit more tricky. A intersection B union A intersection B complementary. So first of all, you have to simplify this expression. You just have to factor out A. So that would be A intersection B union B complementary. In the same manner as you do with simple numbers, that's pretty much similar. This is called distribution. Same logic applies here. And so that would give us A intersection. This is the sample space, which is the set A itself. That being said, the probability of all those complex events comes down to event A, 1 over 13. So that's the final result. All right, let's move on to our next problem. So in this problem, we have a box which have 6 red marbles, or what is that? The balls. The box of balls. Okay, so we have 6 red balls, we have 4 white balls, we have 5 blue balls, and we're drawing one ball at random. And the size of our sample space is given to be 15. So what does this problem ask us to do? Well, it asks us to calculate the following probabilities. So we need to find the probability of drawing a red ball. So how to find that? Well, that's pretty simple. You probably already calculated that. That's basically 6 over 15, which can be simplified to 2 over 5. Nice. For the white, we have 4 over 15. And for the blue, we have 5 over 15, which is 1 over 3. All right, for the next one, we have the probability of complementary of R, which means this is not R. So we're basically drawing a ball. And what is the probability that this ball is not going to be red? So we're going to wind up with a blue or white ball. What is the probability that we're obtaining not red ball? So that's just basically all balls except the red balls. 4 plus 5 over 15, which will give us 9 over 15, 3 over 5, and that's the final result. And for the probability of the event R, which is the red, or this is white, well, that means we have to sum up those probabilities. And if you are attentive enough, you might notice that we don't actually have the probability R intersection white here. This is the 0. It is 0 because we cannot have both the red and white ball at the same time. Those events are mutually exclusive. And so the probability of those events is essentially 0. The probability of their intersection is essentially 0. So we don't need to find that. So that significantly simplifies our problem. We only need to compute 4 over 15 plus 2 over 5, which is 6 over 15. And we have 10 over 15, which is 2 over 3. So this is the result, 2 over 3. And the next sub-problem asks us to find the probability of B given this is not red. What does that mean? You may have noticed that we have only one draw here, so we don't have any consecutive draws. That being said, the problem asks us to find the probability of getting a blue ball given this is not a red ball. In other words, we're limiting the scope of the problem to only blue and white balls. We are excluding all red balls from our sample space. So we're kind of modifying our sample space to exclude all red balls. Imagine you're just taking off all red balls from your box and just throwing them away. What is the amount of blue balls? 5. Over what is the amount of total possible outcomes in our modified sample space? This is 15 minus the number of red balls that we had there but threw them away. Well, this is 6, which gives us 5/9, and that would be our result, 5/9. Alright, that's a wrap for today's video, and I really hope you found it helpful. And if you'd like to keep learning it together, we've got a Discord community where we discuss problems or programming coding challenges. And if you're also into coding stuff, feel free to join our community so we could help each other. You will find the link in the comment section below. Also, feel free to stay connected with me on LinkedIn. In our next episode, we're going to continue solving even more practical problems and challenges on probability theory. So stay tuned. Bye.